Welcome to another in our series of live conversations about science at the edge and how it will continue to change civilization and even what it means to be human. I'm Matt Kaplan, the host of Next, Science People Tomorrow, People Science Tomorrow. Let's get that in the proper order. Here at KPCC, Southern California Public Radio, we're coming to you once again from the Crawford Family Forum in the heart of Pasadena, California. But our topic this evening is one that involves the entire world, as you will hear as we explore tonight's topic of thermonuclear fusion, fusion power, and that long sought-after dream of achieving this for all of humanity. Let me show you a book. This is a book that my parents gave me when I was very young. We'll just leave it at that. It's called Man and Power. It was a little, not politically correct because it came out in 1961. I really loved this book. Thank you, Mom. She's sitting over here. And I still do. It is just the best. It really traces the history of energy from the use of our own muscles through nuclear power. And, that really, when you examine that history of energy, you're really examining the history of humanity, at least from one viewpoint. One very important angle. Now I want to show you a picture. It's in the book, but I think we're going to put it up there on the big screen over our heads as well. There it is. That is the Stellarator. That was an early attempt to create a controlled nuclear fusion reaction. Here is a quote from the book, Man and Power. Much more study will be needed before we can hope to get useful work out of fusion. Perhaps the problem will prove insoluble. Still, fusion power has such attractive possibilities that scientists are unlikely to give up the search for a long time. Every word of that statement written 53 years ago remains true today, except possibly for the part about the challenge of fusion being insoluble. Now, you may not know it, but controlled fusion is happening somewhere in the world nearly every day nowadays. It's happening in some of the most colossal machines ever created by our species, and yet these devices will be dwarfed by one that is already under construction in the south of France. We will see that machine and learn a bit about fusion basics before we meet the first of three outstanding guests that we have for you tonight on this edition of Next. Let's do that right now. We're going to take a look at a video right off of YouTube so you can look at it and show it to your friends and family anytime. We're going to roll that now. Unfortunately, no.
The Sun, like the stars, draws its energy from the fusion of hydrogen atoms. This nuclear reaction is 1 million times more energetic than the strongest of all chemical reactions. Since the early 1950s, scientists have been drawn to this powerful energy source and have sought to recreate it on Earth. The stakes are enormous. Fusion could provide a source of large-scale energy, one that is safe, available anywhere on Earth, in unlimited quantity, and with no negative impact on the environment. The fusion adventure began in the 1950s with a young Russian soldier called Oleg Lavrentiev, who first proposed the idea of a fusion machine based on the thermal insulation of high-temperature plasma using a high-voltage electric field. In the following years, many fusion machines were built and tested in the Soviet Union, the United States, Europe and Japan. These initiatives were triggered by the first major oil crisis. The hunt for a new energy source had begun, both in the public and the private sectors. Despite the progress, it soon became clear that when it comes to fusion, size matters. A bigger machine was needed. Through the ITER project, 6 nations, China, India, Korea, Japan, Russia, the United States of America and the European Union have agreed to pool their financial and scientific resources to prove the viability of fusion as an energy source. ITER is the Latin word for the way. Its goal is to pave the way to fusion power. From 50 megawatts of input heating power, ITER will produce 500 megawatts of thermal power for at least 300 seconds, the first fusion machine to produce net energy. The chosen site was in southern France. And so, here we are today, building the largest fusion machine ever. ITER is based on the Tokamak concept of magnetic confinement. First, the fusion fuel, puffs of deuterium and tritium, is injected into a vacuum vessel. Then a powerful magnet, centered in the core of the machine, is turned on, inducing a current across the gaseous mixture. The voltage rips electrons from the atoms, forming a particle soup called plasma. Now the superconducting poloidal and toroidal coils are ramped up, locking the plasma inside the vacuum vessel. Squeezed together, it quickly heats up to 10 million degrees centigrade, but that is not good enough yet. To make the particles fuse, the temperature needs to be increased further. Radio and microwaves are fired into the plasma together with high-energy beams of deuterium atoms until the plasma reaches 150 million degrees. Hot enough. The products from this reaction are helium and highly energetic neutrons. While the helium particle remains in the plasma, helping to keep it hot, the neutrons escape the magnetic confinement and hit the surrounding metal wall. Once they have slowed down, the neutrons release their energy by emitting heat, which is finally turned into electricity. While work progresses in southern France, manufacturing begins in ITER member factories all over the world. Instead of providing the monetary value of each system or component of the ITER machine, the member states will deliver the completed components to the ITER site, where they will be assembled in what is certainly one of the most complex jigsaw puzzles ever conceived. The largest components will arrive by sea and be unloaded near Marseille. From there they will travel to ITER along the 100-kilometre ITER itinerary, which has been especially adapted by France to receive the exceptional size and weight of the loads. The delivery of the first completed components is scheduled for 2014. From that moment on, approximately 6 years will be necessary to complete the assembly, testing and commissioning of the machine. Back at the construction site, mighty bulldozers and towering cranes dominate the scene. Just a few years from now, ITER will tell us if the dream of a limitless energy source can finally become reality. The 35 nations united under the ITER flag believe that fusion is the future. And so do we.
So a good introduction, at least to that device, which is, as you saw, under construction in France. And as you saw, the United States is a partner in the ITER project. The man who heads that effort here in the U.S. is with us here tonight, at least virtually via Skype. Dr. Ned Satoff is a plasma physicist. Prior to establishment of the U.S. ITER, and that's how we say it, over there they say ITER, the U.S. ITER Project Office, Ned was head of the off-site research department at the Princeton Plasma Physics Laboratory, where he managed research at leading facilities around the United States and the world that are addressing key fusion physics and technology questions. He achieved his PhD in astrophysical sciences from Princeton back in 1975 and was already doing fusion research then. Dr. Satoff was president of the Institute of Electrical and Electronic Engineers in 2001. He also served as the IEEE's vice president for technology policy. He is a fellow of the American Physical Society and the American Association for the Advancement of Science. Please help me welcome, as I said, via Skype, Ned Satoff.
Thank you. It's a pleasure to be here.
And we're glad to have you. Ned, and when we were talking on the phone the other day, you pointed out that really everything we do here on Earth has always been based on fusion power. We all live on fusion power, don't we?
Well, I think that that's at least 90% true. Actually, it's probably 80% true in the United States because we have 20% power coming from fission. But I think that if you went back to that book that your parents gave you, Man and Power, and you go back to the first caveman, he was feeling the heat and seeing the light that came from an object called the sun. He was probably surprised to see it come up every morning. But nonetheless, what he was seeing was the thing that powered much of this Earth for millions and millions of years. And if you look at the fossil fuels like the coal and well, let's take the coal and the oil, they came from plants that were grown millions of years ago, and they grew because of solar energy. So in fact, we have to go back to the sun and ask where it gets its power. And actually, if we go back, and you actually had a few slides I sent you, if you showed the first one, which had the sun, I mean, what we're looking at there has been something of a mystery for over 100 years. As a matter of fact, if you went back to about the year 1900, there was a big scientific question about how can the sun keep burning that long? There were a variety of models of how the sun burned, and if you thought of it as oil and somehow got enough air to burn all that oil, it would have run out of fuel something like 100,000 years, something like that. There were other models Lord Kelvin came up with where it was a gravitational object that was contracting. And there were ideas of a big solid liquid, hot liquid that was radiating and slowly cooling down. But those models came up with a sun which might burn for 20 million years. Now we know that the sun has been around burning for almost 5 billion years. So there's a big factor there. And the big factor comes from the difference between chemistry and nuclear. So in chemistry, what we're seeing is the electrons bouncing around and moving in various energy levels as they orbit around a nucleus. And that gives rise to energies which are a few, let's call them electron volts. If we look at a nuclear reaction, be it fission or fusion, we get about 1 million times more energy per reaction. And that is how the sun keeps lit. If it were chemical reactions on the sun, it would have long since gone dark. And what we're seeing now is the fact that the sun is powered by nuclear reactions, which get, as I said, about 1 million times more energy per reaction than would happen if it were chemical.
You've got a couple of slides, in fact, that we can go to actually show some of the basic physics behind fusion. We can bring up the first of those here. Ned can't see them. What he also can't see, Ned, we do have a full house here in the Crawford Family Forum listening to your words.
Okay, great. Well, on that first one, which shows the sun, I had another point to make. And that is that if you look at this relatively high-resolution picture of the sun, you'll notice that the sun is not a calm, uniform, spherical object. It looks like it's boiling, like the bubbles that come up and the convective cells that come up when you boil water in a pot. And it also has these loops sticking out. And what we're seeing there is a process where the heat is coming from the inside of the sun. As a matter of fact, if you look at what fusion reactions are going on in the sun, it is burning about something like 600 million tons of hydrogen every second. And it's converting about 4 million tons of that every second into energy. Just like Einstein said, he can turn mass into energy. What's happening is about 4 million tons of hydrogen is being turned into energy every second on the sun. And that is what is causing the heating. And matter of fact, if you look at the sun, it's about 75% hydrogen and it's about 25% helium. And helium is what comes out of the fusion reaction, as we'll see in a future slide. But also, if you look at this picture of the sun, you'll see those bright loops sticking up. Those are probably among the hottest things on the sun, much hotter than the rest of the sun. And they are this hot plasma following a magnetic field line, which is sticking up and then going back down into the sun. So whereas the sun is mostly confined by gravity, because its mass is about 300,000 times that of the Earth, there is also a component of magnetic confinement on the sun. So what we are trying to do with ITER and with Tokamaks in general is to use that magnetic confinement principle that we see in those coronal loops on the sun, and we want to bring that down to Earth. So if you went to another slide, you mentioned you had some of the cartoons. What we're trying to do is to turn hydrogen into helium. And you know that hydrogen comes in a few flavors, let us call them isotopes, and they differ by the number of neutrons. Now let's not get caught up in the details, but it turns out the highest octane fuel for a fusion reactor, so to speak, is a mixture of deuterium and tritium, about a 50-50 mix. And I don't know if you can hit the right arrow and get that animation going, but it would show that when deuterium and tritium collide, what comes out some of the time is a helium nucleus and a neutron.
We just watched that happen on the screen here.
Okay. Well, when you have a magnetic field, it can confine electrically charged particles. And deuterium, when it loses its electrons, is positively charged. Tritium, when it loses an electron, is positively charged. And the helium, when it loses its 2 electrons, is positively charged. And they remain confined by this magnetic field. The neutron comes shooting out because it's not contained by the magnetic field. So that leads us to the next slide, where we see some of the loops that are involved in fusion. So as you see at the center, we have a nucleus of deuterium colliding with a nucleus of tritium to produce this compound nucleus that then splits into an alpha particle and a fast neutron. Now, what's the problem here? The problem is that those deuterium and tritium nuclei are both positively charged. And positively charged or similarly charged particles repel each other.
Just like the poles of a magnet.
That's right. And so what we try to do, except it's an electrical force instead of a magnetic force in this case. And what we try to do is to get the deuterium and tritium so close together that they'll stick. Okay? And that's let's call it a millionth of a centimeter apart. That's about how close they have to get. Now, in order for them to get that close together, they have to have a lot of energy or they would have bounced off. So if you have that amount of energy, that corresponds to temperatures of about 100 million degrees centigrade. And that is why we have to have this really, really hot soup, which is the medium in which we have these reactions occur. So the trick is to heat up the soup of deuterium and tritium, to have it cook, and when these reactions occur, you want the alpha particle, which gets 3.5 million electron volts. Remember, that's 1 million times the energy that comes out of a chemical reaction. And it gets trapped by the magnetic field and circles around and heats up more deuterium and tritium. So that's how we keep it heated. And that's what's called a self-heated plasma. And that's what we're striving to do. We're trying to create a self-heated or a burning plasma. Now that neutron that comes out is not charged. And it comes out with about 14 million electron volts. And the way we have a relatively self-sustaining reaction is we have to produce some tritium. And so the way we produce the tritium is having that fast neutron hit some lithium, which is used as a coolant in the device, and it then transmutes the lithium into tritium, which we then inject back in as fuel. So the real raw materials of this fusion reactor are deuterium and lithium. Okay, so, and they are quite plentiful. Both were produced in great abundance at the Big Bang many, many billions of years ago. And what we do is create that rare tritium nucleon by having a nuclear reaction from the fusion neutron. So that's the nuclear chemistry, so to speak. And now we have to figure out what sort of a bottle to use in order to contain this hot gas. And that's shown in the next picture, which starts out with star in a toroidal magnetic bottle. That is what's called a tokamak, and you can see those big blue magnetic field coils. They produce fields that are like 100,000 times the field of the Earth, and they serve to tell the plasma that it ought to be a donut. It ought to wrap around within those magnets. And then you see the ones that are called outer poloidal field coils, and you see an inner poloidal field coil. These are the ones that cause the plasma to carry current. In the case of ITER, about 15 million amperes of current, which is to be contrasted with like 1 ampere in your electric light bulb. So we can put about 15 million amperes through that plasma and heat it up so that it becomes a good target for heating systems. Now, if you go to the next picture, called magnetic confinement, is well studied around the world, you'll see a few devices. And some of the other speakers you have for this program are well acquainted with some of these devices. Like D3D is a device at General Atomics, where one of your speakers, John Parmentola, is the senior vice president, and he runs that program, among other things. Alcator-CMOD is a device that is at MIT, and it is a very high field magnetic confinement device, so it goes at high density. The NSTX is a lower field device at Princeton, and it studies a configuration where the hole in the middle of the donut is relatively small, called a spherical torus. At the right-hand side, we have a device called the Joint European Torus, which is one of only 2 devices, 2 tokamaks in the world that have burned deuterium and tritium and produced power. One was the Tokamak fusion test reactor at Princeton, and it got shut down in the late 90s. And then there is the Joint European Torus, which has continued to be upgraded since its origin in around 1983, and has produced the record amount of fusion power from a magnetic confined system. If you look across the bottom, you'll see some newer devices, like the JT60 is an extensive upgrade of a Japanese device, which was a companion of TFDR and JET, that era, and now it's being really, really upgraded based on a collaboration between Europe and Japan, which, believe it or not, was part of the deal of ITER being sited in Europe. Europe agreed that it would help Japan build a companion device in Japan. So it was a part of a deal. Okay. EAST is a new tokamak in China, K-Star a new tokamak in Korea, and Aztecs a middle-aged tokamak in Germany. So you can see that these sorts of devices are all over the world, and they are studying the reactions and the confinement principles that we'll use in ITER. If you look at the next slide, which is numbered 6, fusion power already demonstrated in tokamaks. This is the inside of the 2 deuterium tritium burning devices. One is TFDR at Princeton, which in 1994 produced 10 million watts of power. Like that would be equivalent, well, let's see, 100 watts is a light bulb. 10 million watts is what we produced here. So it's many, many, like 100,000 light bulbs. If you look at the Joint European Torus, it edged out TFDR in power a little bit, okay, but it came in later. So it did 16 megawatts of fusion power. So if you ask, has fusion power in a magnetically confined system been shown to be possible? Yes, it has been done. It was done in the 90s, both in the United States and in Europe. The next slide shows what we're building in France. That's the core of the machine. At the center is the donut, which is pink plasma in this case, and the variety of magnets and plasma-facing components and the like in that core. If you go to the next one, you see some of the parameters, like how much that core weighs. What you see in the solid part of this picture at the center is, first of all, a big stainless steel container that's about 30 meters tall, about 30 meters in diameter. That's a great big thermos bottle. So it's what's called the cryostat.
And I think we're going to hear a lot more about that from John Parmentola, because that's being put together there.
You'll also hear about the spark plug that goes through the middle of it, called the central solenoid.
I also want to make sure we point out that so no one misses it. Just for the scale, look at the little human figure there down at the bottom. And that'll give you an idea also of the scale of this device compared to those you saw just a few moments ago on Ned's previous slides.
Right. So this is the core of the machine. And what ITER intends to do is to produce 500 million watts of power from the fusion reaction with only 50 million watts of power going in to heat it. So that's a gain of a factor of 10. And that is going to really prove that we can actually produce power. Now, it's not producing more power than comes out of the wall plug that you use to get the heating systems, but if you look at the plasma, it is producing more fusion power than it went into it when it was being heated. If you go to the next slide, number 9, that's faintly in the right, that's a picture of the ITER site as it is almost today. And you see across the bottom the flags of the partners. Let me just tell you a brief story of how this started. It was 1985, and President Reagan and General Secretary Gorbachev of the Soviet Union were having a rough time at a summit meeting. And the science advisor to General Secretary Gorbachev said, "We need to come up with something we can agree on. Why don't we jointly design a fusion reactor?" Okay? And so this came back to President Reagan's National Security Council, and overnight, the CIA and the Defense Department battled it out as to whether or not this was a good idea. But in the end, they agreed that they would pursue this, and it took them about 3 years to agree. And during that time, Japan and Europe joined, such that in 1988, there was what was called the conceptual design activity, where those 4 parties tried to do a design of the device, a cost estimate, and the like. And they did a good job through about 1990, 1991, at which point the Soviet Union had fallen apart, and there was a delay of about a year as the Soviet Union turned into the Russian Federation. And then those 4 partners continued. And so the United States, Russia, Europe, and Japan did an engineering design activity that started around 1992 and proceeded through 97, 98, at which point there was a cost estimate wherein the U.S. thought it was too expensive and pulled out at congressional direction. But then in 2001, the U.S. fusion community started a series of community studies of, are we ready to proceed to burning plasmas? Are we scientifically and technologically ready? What would be the benefits? Would the benefits be worth the cost? And what are the different approaches and the pros and cons of doing the approaches? So that then led to various technical assessments. We had a big meeting with over 200 people in Snowmass, Colorado in the summer of 2002. There was then a National Academies of Science and Engineering report entitled Burning Plasmas, Bringing a Star to Earth, in which people not involved in the fusion program, people of the order of Nobel laureates in a variety of scientific fields, concluded that burning plasmas were a highly promising area for research, that it was very relevant to providing the understanding of the core of an attractive fusion reactor, that it would significantly reduce the risk that industry would have to face in building a commercial fusion reactor, and that we should proceed, and we should proceed by the U.S. joining the ITER collaboration. So in January of 2003, President Bush announced that the United States would join the ITER negotiations, and within a matter of weeks, Korea and China joined. 2 years later, India joined, and that then brought to 7 the number of partners that are in our collaboration. So in the period from 2003 to 2007, we divided up the device into 180 some pieces and assigned a value to each, what percentage of the machine was each. And then we assembled in front of each of our delegations a list of what are the things that each delegation would build and then bring to the ITER site to be assembled and operated.
And Ned,
And that's how it all worked.
only because our time is flying by so quickly. I'm going to ask if we can, I know you have another slide here that shows the ITER site very close to the development level that it is at today. And if we can jump to that, and then a lot of these, this is bringing up so many questions that I hope we'll have some time to discuss when we have our other guests up here as well.
Okay, so this is slide 10. What you're seeing there is the flattened area which France has provided. And at the very, well, in the foreground is the headquarters building where there is an office for about 500 scientists and engineers. And then above that looks like a hole in the ground. That is where the tokamak will go. We'll have a close-up of that on the next slide. And behind that are two buildings. The one on the left is what's called the cryostat building. And that's where India is welding together the parts of that big stainless steel thermos bottle that I talked about in the very beginning. It's too big to ship it by road or by air or by sea, you know. So they're bringing it in parts and then welding it together in that cryostat building, and then it gets shipped in big pieces into that hole where the tokamak is being built. And the building to the right of that is called the Toroidal field coil building. And that is where Europe will be building those magnetic field coils, which are also too big to ship. And so what we see here is that there are some components which are too big to ship, and they will be built largely at the site. And then there are big objects, such as the U.S. is providing, some huge drain tanks for cooling water, and some big magnet components, where France had to go and modify the roads and the bridges between the Marseille port and the ITER site so that these big components could be shipped from the port at Marseille and Fos to the ITER site. They do that overnight. There's a big disruption of the traffic pattern in that area, but France, as the host, has committed to provide that transportation. And so Europe pays for that segment. And they've modified all the roads so that it can handle these very heavy shipments. If you look at the next slide, number 11, that's that hole in the ground. That is where the tokamak itself will go. This is a building that is built inside of a building. Part of the site requirement was that it had to be largely earthquake-free, and that part of France still has earthquakes. And so what the French have done is they've built a building, and then they put 493 seismic isolator posts down. They are flexible members that can absorb the motion that's associated with an earthquake. And then what we see above of that is the steel reinforcement that will be part of that basement floor on top of those seismic isolator posts. So this summer in July, we're expecting to pour the concrete on that reinforcing steel, and that will be about 1.5 meters thick, and will support that vacuum thermos bottle that I described, and that will support the tokamak, and that is where we intend to produce the first industrial scale, reactor scale fusion power system on Earth.
It is a magnificent effort by a good part of the civilized world, and we will talk much more about ITER later on in this evening's discussion. But one of the precursors to ITER is not very far away from us right now, and I got to visit it just a couple of weeks ago. I drove down to the beautiful La Jolla campus of General Atomics to visit a machine called the D3D. You saw it on screen a few moments ago. Along with the men and women down there who are using this reactor, who are getting us closer to the goal of controlled fusion power. And a lot of what they're learning, I think Ned would say, is going into the design of ITER. Here is a very rough video that I shot when I was down there walking around this Tokamak reactor, this fusion reactor. And I can tell you it was very exciting to me, as you'll see, to get up close and personal for the first time with one of these devices. We can look at that now.
This is the Tokamak. The toroidal field coils, you have 6 of them in a bundle, so there's 24 of these bundles around. between the bundles we have diagnostics. This can put up to about 5 megawatts of power. There are 4 of these. Let's walk.
I'll follow you.
All around the north. Be very careful. Hold on to this.
Okay.
We'll walk at the same time. Okay.
Stop you for a second, because I got to tell you how much I feel like a kid in a candy store. Because I've been following the development of this technology for so many years. And here it is. This is where you guys have harnessed the energy of a star.
Exactly.
When you talk about the kind of current, the amperage that you have to put into here, where do you get it? I mean, how do you build that up?
We have a motor generator that sits outside that drives the current through the coils. What's the size of the motor generator?
525 MPa.
520 megavolt amperes. So you spin it up for a few minutes, and then for 10 seconds you pull the current out and drive the current in coils. These, we have 138 kilovolts comes in, and we take power directly off the grid. Which San Diego line.
Yeah, SDG&E must be a big fan of yours.
Be careful.
No problem. You gonna close that door?
Yep.
So that must be somewhat reassuring to know you've got that kind of shielding between you and
Yeah.
a whole bunch of neutrons.
Well,
racing
you know,
around.
at the site boundary, we get what? About 20 millirims a year.
Something like that, pretty low.
Yeah.
You know, and it's not, you get a couple trips across the U.S. and you get more than that.
That's right.
So they're doing experiments this afternoon.
So there was fusion going on there moments before we...
Exactly. We named all our gyrotrons after characters. So there was one long ago named Dorothy.
I don't think we're in Kansas anymore.
No. These are the screens and oscilloscopes they use for the
You may think that's the
microwave
control room for the reactor.
We
It's
have
not.
6 devices that are called gyrotrons that generate high power microwaves. And
meetings. Up to 1 megawatt each.
1 megawatt, that's huge.
Yes.
So we end up injecting a lot of megawatts into the machine. And as with your microwave, we end up heating up the plasma a lot when we are launching.
Oh my goodness.
So that's what a 5 Tesla field feels like on the outside.
And that was just the microwave control room and some of those big microwave generators where they inject some of that energy into the Tokamak, the D3D. You will see the real control room in a few moments. And I just want to say I'm really grateful to my tour guide there, Tony Taylor, and all the other great folks that I met during that visit. They all work for, except the scientists who come in from outside institutions, they work for the guy that we're going to meet next. Dr. John Parmentola is Senior Vice President of the General Atomics Energy Group. This kid from the Bronx got his PhD in physics from MIT, and like Ned Sadoff, he has more eye-popping bullets on his resume than we have time to mention. But here are a couple more. He served as Director of Research and Laboratory Management for none other than the U.S. Army. Prior to that, he was Science and Technology Advisor to the Chief Financial Officer of the U.S. Department of Energy. John was Executive Director of the Panel on Public Affairs at the American Physical Society and a postdoctoral fellow with the Program of Science and Technology for International Security at MIT. Please help me welcome John Parmentola. And John, you can just, we'll make that, Dave will adjust that for you a little bit there.
Thank you very much for the kind introduction.
You're very welcome. My pleasure. And thank you for joining us here this evening, as I said. That's quite a facility you have down there.
Well, you know, when I came to General Atomics, I knew some things about fusion. And over time, the people there that dedicate their time to not just running that facility, but also doing research to help us understand how to realize fusion. D3D is quite a remarkable facility. In fact, if you look at the inside shape of D3D and you blow it up, that's ITER. So ITER was inspired by D3D. And so it's been a workhorse for the community for nearly 30 years. And we have collaborations with researchers from all over the world. We have about 100 users that come to D3D to participate in experiments. We also work very much with the Chinese in East. So it's an exciting place, a very busy place.
Awful lot of the fusion research being done around the world where these devices are national laboratories in the U.S. or universities. General Atomics is neither of those. It's a private company.
Yeah, it's very unique in that General Atomics, I think, is the only organization on the planet that does both fission and both forms of fusion. Today we're talking about magnetic fusion, but there's also inertial confinement fusion. And in fact, California is the fusion state, whether you know it or not. D3D is the largest tokamak in the United States, and the National Ignition Facility at Livermore is the largest inertial fusion facility in the world. And so we lead the world in fusion.
And I want to come back to that other technology for making fusion happen in a minute, which is also something GA is involved with. You also have some slides, and I thought if we can start with slide number 2, because your slides help demonstrate the need for these new sources of energy and why fusion may be such a good solution, or at least part of the overall solution. What are we looking at in this first one?
Well,
you've got it down there at your feet.
Let me say something. I think my role here today is to try to paint the context for why it is that we need to be concerned about the future of energy. Energy drives everything that we do. No matter what you do, it involves energy. And so we normally don't think of energy as a national security issue, but it is. Without it, we cannot be an industrial country that leads the world in technology development. It is not possible. It enters into food production. Everything that you can imagine involves energy. So the first slide has to do with a challenge that we'll have by 2050. And so if you look, I guess, over to your right at the vertical axis, you see where the blue starts, the deep blue. That starts at 1,000 billion watts of electricity. That's the peak electricity that the United States produces every day. And that electricity production, if we follow the age of coal plants that will be decommissioned, and we follow the fission reactors that will be also decommissioned by 2050, you see that white area widening. You also see the green area. That green area makes an assumption, which is a very modest assumption, that U.S. electricity demand will increase by 1% a year between now and 2050. So if I take the demand and I look at the decline, by 2050, I will be short 55% in electricity. So now it begs the question, where am I going to get it from? So if you think about it, the only things that will be available are natural gas and renewables. It's hard to imagine that a major country like ours will be able to base its strategy into the future based upon that.
And what isn't even touched on here, this is just the energy that we need no matter what the source, is the fact that so much of that blue area, that existing capacity, is what has the, seems to be headed toward killing our planet, or changing our climate at least.
Yes. The other thing I didn't point out is that I said 1% per year. So if you take 1% of 1,000 billion watts of electricity, that's about 10 billion watts of electricity. If you look at the world will need 50 times that every year. 50 times that. It's enormous. So in the world that we're going into, with population growth and developing nations becoming developed, the demand for energy will increase dramatically. And we have to figure out a way of supplying it. Now, when you make that statement, it begs a question, well, where are the resources? Where do I go find the resources to do this? Next slide. So in this slide, you see that little circle over there. And the little circle is based upon proven reserves. This is what we know today exists. So the black is obviously coal. The orange is natural gas. The green shaded area is oil. And then you see a little sliver, and that little sliver corresponds to uranium thermal reactors. It's really small, and you wonder, why is it so small? Well, it's not because there isn't energy in the resource. It's because the way we try to extract the energy from it is very, very inefficient. So coal, for example, if I put it in equivalent barrels of oil, is about 4.2 billion barrels of oil equivalent. The energy that I extract from uranium with current reactors is about 370 billion barrels of oil. No, coal is 4.2 billion barrels. So the uranium that itself is being inefficiently used as a source of energy. But if I change the nature of the reactor that I use, and I go from a thermal reactor to a fast reactor, you see the slide, the circle on the right. That's your left. The yellow is uranium, the same uranium that was in that white area, that little sliver. Mm-hmm. But if I extract the energy efficiently, I can get an enormous amount more of energy out of it. And the part that's green, that's thorium. And thorium is also a very abundant energy source in the United States, by the way. And so if I take that, I have about 200 trillion barrels of oil equivalent. So the size of the resource that I have is enormous. But I need the right technology in order to extract it.
And I saw some interesting technologies as a sidelight when I visited General Atomics the other day that are moving us toward this better use of fission power. But fission power brings its own challenges and difficulties, right, of course. Your next slide brings us right back to fusion.
One thing I should point out, that if you base the amount of energy on that one big circle and you use as a measure the world's consumption of energy per year, which is 500 quads, or 500 quadrillion British thermal units, that energy would last you 2,000 years. Mm. But with fusion, it's a completely different ballgame. So as Ned Sartoff pointed out, the way we extract tritium or produce tritium is from lithium. And if you add up the proven lithium reserves, that's about 1,600 trillion barrels of oil equivalent. And that would last, these are just proven reserves, that doesn't deal with other reserves we'll find. That would last you 16,000 years at world energy consumption. So the resource we have in fusion is an incredible resource, It's also very safe. The nuclear waste from it is far different and far less than that of a fission reactor. We can produce our own fuel, as Dr. Sartov pointed out, from lithium. So in essence, we have maybe not quite an inexhaustible resource, but we have an enormous amount of energy that we can produce from it. Mm-hmm. So it has all the features that one would like to have in an energy resource: abundance, safety, limited nuclear waste. Why don't we move on to the next slide?
And if we can skip ahead maybe 2 slides.
Yeah, we can skip ahead on this one.
You show this one, which is a pretty impressive comparison.
Okay, so if you were to produce 1,000 million watts of electricity for a day, you might ask, well, how do I produce that, say, with coal? This is just one day. You need 18 million pounds of coal. That's 80 times an individual rail car of coal just for one day to produce 1,000 megawatts of electricity. Well, what do I need from a fusion plant? Well, I need about a pound of deuterium and 1.5 pounds of tritium. That's like 3 water bottles full of deuterium and tritium. That's all I need. Waste produced from a coal plant in one day, you produce 60 million pounds of CO2, 1,200,000 pounds of sulfur dioxide, and 160,000 pounds of nitrous oxide. From a fusion plant, I produce 2 pounds of helium, if you consider that to be waste. So that'll fill up about 400 balloons. That's all that'll do. So,
and I think a point to be made about this is that even when the tokamak, like ITER or like D3D, is operating, when the plasma is racing around in there, it's still a pretty good vacuum, isn't it? There's almost nothing in there.
Yes. And also, as I say, it's safe. I mean, if the plasma were to, would quench, there isn't enough energy there to cause problems. We know how to deal with it. Mm. You know, it doesn't have the radionuclide gaseous emissions that would come out possibly out of a nuclear plant if the vessel were to be breached.
Yeah,
the
no
containment
meltdowns.
The containment were to be breached. So those things are very difficult. And by the way, contrary to what everybody says, fission reactors, modern fission reactors, are very safe. Okay, so I'll debate anybody about that. They are very, very safe.
We'll pick that up on another evening, maybe in the next series. You've got a slide I want to talk about, because it shows the steady progress that has been made toward, well, the next big step will be ITER, I suppose.
Right. So as Dr. Sartov pointed out, you had TFTR at Princeton and JET. Both of these accomplished very significant milestones in fusion power. Each produce more than 10 million watts of thermal power. They weren't producing electricity, but they weren't designed to produce electricity. And the graph that you see to your left is an interesting graph. And the reason why I say it's interesting is that if you follow your eye along that plot of those colored objects, it roughly forms a straight line. And there's an interesting history behind this straight line. Usually what this means is that you are embarking on a paradigm-shifting technology. So for example, if you were to go back in computing and go back to the turn of the last century, where we did mechanical computing, and then we went and we built machines that did computing, and then we went to electric switches that did computing, and then we went to vacuum tubes and so on. Each of those corresponded to a shift from one technology to the next. But if you plot computational power as a function of time on a plot like this, it forms a straight line. Mm. And that indicates that you're on a paradigm shift with regard to computation as you're going along this path. Now, the thing that stopped all of this was the fact that we ran out of machines. There's a gap between the year 2000 and current because there isn't any machine available to take us to the next level. But if we start from 1970 to 2000, the amount of power that we've been able to produce has increased by a factor of 1 trillion. Okay? So from meager beginnings, we've advanced the power production by a factor of 1 trillion in 40 years.
Finally, something to parallel the advance in computing power,
yes,
computational power.
Yes.
Yeah.
So an ITER is designed to produce 500 megawatts thermal energy with 50 megawatts of input energy, which means that it will produce a net gain in energy, and it will demonstrate a burning fusion plasma. That's what it will do. This will be a major accomplishment, but there's still things that need to be done.
Yeah, you were talking about this on your next slide. There are a couple of holes, even with ITER, that you feel there are holes that need to be filled.
Yes, we need to be able to do some other things in order to reduce the risk in fusion energy. So now you see off to your right a picture of the Earth, and all of those facilities that you see there were facilities that Dr. Sartov basically talked about in that one slide. So this is a world activity that's going on to get us to a burning plasma. And of course, ITER, which will be a high gain burning plasma, will take us a major step. But is that all we need to go to a power plant? There are a number of things that we need to address in addition to a high gain burning plasma. And Dr. Sartov indicated in his talk that we can produce our own fuel. Well, if you go to the open market and ask, what does a kilogram of tritium cost you today? It costs over $100 million. It is scarce. Why? Because it's not a natural substance. We have to produce it, right? And of course, we used to produce a lot of it when the weapons program was very active, but we don't produce it today, although there are nuclear reactors that do produce it. But what we need to do is we have to demonstrate that not only can a fusion reactor produce its own fuel, but we can produce it cost effectively. Otherwise, your price of electricity will be very, very high. So what do we have to do? We have to show that we can reduce the price of electricity by about a factor of 100. So if we can produce it for about $1 million per kilogram, that's within the range of getting to an affordable cost for the price of electricity.
For tritium, yeah.
Yeah, for tritium.
And what's the other thing that we need to figure
so
out?
So as Dr. Sartov pointed out, there are high-energy neutrons that are produced by a fusion reactor, fusion reaction.
Mm-hmm.
Well, those neutrons can cause damage in materials. And we have to do work on materials to ensure that we don't have to change out the materials in the fusion reactor too frequently. Current estimates are that they could last probably 3 or 4 years, but we'd like to get them to last longer. The longer they last, the better it is, because you have to shut down the reactor, you have to go in and take out all of those materials, which are quite significant in terms of taking them out and replace them all. That makes the reactor unavailable.
And this is all about making this technology, because it does seem that it's going to work, making it economical enough to be competitive.
Correct. So the other thing is, which people don't always pay attention to, is efficiency. So I have this high-energy neutron, and I want to get as much energy out of it as I possibly can. As Dr. Sartov pointed out, when that neutron impacts the walls, and then there's another section of the reactor called the blanket that contains the lithium and some other elements, that neutron comes in, hits the lithium, produces tritium, but what it also does is deposit heat in that medium. And I have to extract that heat at high temperature in order to increase my efficiency. This is something we know from thermodynamics that's over 150 years old.
Same thing that happens today in fossil fuel-powered plants, right? You want to get as much of that heat turned into steam to run your turbine as possible.
Correct. And so there are materials issues there because the lithium is in a kind of a liquid soup, and it's at high temperature, and we have to put a thing in there called a heat exchanger, which will able to take the heat, transfer it to a gas like helium, and that helium can drive a turbine generator to generate electricity. And we like to do that at very high efficiency. And efficiency is very important because for every percentage improvement in efficiency over the lifetime of a reactor, you're talking about billions of dollars in revenue, not millions of dollars, billions of dollars. And that, of course, is very important to the investors that will invest in this to produce electricity and make money. So the higher the efficiency, the more revenue that they can generate. And that then makes fusion more economical.
Our time is flying by. Just say a quick word about those two other devices that are on your slide that don't exist yet.
Okay, so we're collaborating with Oak Ridge National Laboratory, it's where Dr. Sartoff is from, on that United States cartoon there. That's called the Fusion Nuclear Science Facility that will resolve these last three issues. And in China, they have their version of that they're pursuing. And in order for us to get to that power plant, we need either and one of those devices to resolve those three remaining issues to get us to net electricity.
Yeah.
So that's where we have to also spend some time trying to influence our friends in D.C. to understand that the future of our energy needs rests with investments like this.
We got to get our third guest up here, but you've got one more slide that I want you to be able to talk about, because this is also something that Ned South talked about.
So right now, fusion, I would say, is plausible. ITER's job is to demonstrate feasibility, and that is through a high-gain burning plasma. That will be a major advancement, and that is really ITER's mission. Now, one of the things at General Atomics that we are actually fabricating down in Poway, California, which is a county next to San Diego, we have a special building there, and we're making what is called the most critical technology that goes into ITER, which is the central solenoid. That's the set of magnets that drives the current that you saw in that cartoon around the donut.
And that's what's going to go in that thermos that's being built now at the ITER site by India?
Correct. And so what you see there is a cylinder. It's a solenoid. It has 6 magnets in it. Each magnet weighs 110 tons. And so we will be fabricating those in Poway, and then those will be shipped by boat to Marseille and then go by that route to Cadarache, France. And we actually have a special facility in Poway to do this because these magnets are extremely heavy, as I've indicated, and we had to have all the floors reinforced in order to be able to do it. We will accept the conductor. The conductor comes from Japan. The conductor alone is about $250 million.
And the reason it's so expensive is this is superconducting. That's why it's got to be in that thermos.
Yeah, and each one of these magnets has 4 miles of this stuff that goes into it. And we wind it there into these magnets, and they're insulated, and epoxy is applied, and they're put into a oven where it's heated and so on. Yeah. So it's an exciting project that we have.
It sure is. I have so many questions that I'm probably not going to be able to get to. But one thing that I still want to do before we bring up our third guest, and it'll only take about a minute, is take us back to D3D, because I did a little bit more video as the Tokamak, the reactor, was actually in use, what they call shots, those little 5 or 10 second periods in which the reactor is actually conducting fusion inside that torus or toroid. So let's take a look at that video, and then we'll get our third guest up here.
Yeah, we should go without him.
I will tell you when he's back, okay?
Roger, thank you.
So this is the real control room.
Mario, no, 9
Ready to fire, 20 seconds.
20 seconds.
That's the guy in charge.
5, 4, 3, 2, 1. Shot in progress. Shot complete.
I'm wondering if we should move the feedback start. The feedback is not starting until 2 seconds there. So
You can start shading from the band.
and so that's what this waveform is right here. It has a little drop that we're going to try to avoid on the next shot. We're going to try to make it go.
Bill's going to be here, so if you still want to test it.
How many shots will you do today?
I'm going to go.
Hopefully on the order of 15 to 20.
So Tony Taylor, my tour guide on your staff, he said that real-time display that you saw of the plasma inside the reactor, you saw that cross-section of the torus, he said that when he started, it took a day to compute what that plasma had done for each shot. Now it takes 2 milliseconds. Pretty impressive advancement.
Well, modern computation has advanced tremendously since the 1950s. And so today we can do things with computers that boggle the mind.
Yeah.
You know, so, you know, you have more computing power now in one of those cards you buy, birthday cards.
That's right.
That existed in a mainframe computer back when I was a graduate student at MIT. So things have changed dramatically over a number of decades.
You saw there were a bunch of people sitting at consoles there or at desks, and a lot of them were researchers, scientists who are using the D3D to conduct their research. One of those scientists is our third and final guest here this evening. He is UC Irvine professor William Heidbrink, and his field is experimental plasma physics. Like Ned, he got his PhD from that little East Coast school called Princeton, where an obscure professor named Albert Einstein once worked. He was named a Fellow of the American Physical Society in 1996, and in 2004 he received the Excellence in Plasma Physics Research Award from the Society. He still does some research, I think, at his alma mater, using yet another fusion machine. You saw a picture of it, the NSTX. He's one of those two rare academics who enjoys teaching both grad students and those big introductory courses that other folks take. And I really love this. He trains undergrads to demonstrate physics at elementary and middle school assemblies. That is something that I did when I was an undergrad at UC Irvine. That was approximately before the invention of the atom. Would you please help me welcome Bill Heidbrink, and go Anteaters. And Bill, as soon as we get the microphone adjusted there, thank you, Dave. So you're one of those guys who goes down there periodically, right, to D3D?
Yes, like Jeremy was talking to you. He was the session leader, and I was just the session leader a couple of weeks ago for an experiment that I was working on there.
Every scientist that I talked to, every scientist and engineer that was down there, there was no question in their minds that ITER will achieve at least a good piece and maybe all of what it is predicted to do, which is, as we heard from Ned, generate 500 million watts, 10 times the power it takes to run it. Do you have any doubt that it's going to do what it's supposed to do?
Well, those of us who are practicing experimental scientists are well aware that things don't always go exactly like we wish. So I think that the probability is extremely high that ITER will achieve that, but I would never say it was 100%. There's plenty of things that don't work exactly like you anticipate beforehand. Anybody who's ever been in a lab knows that well.
You're a good scientist to say that, yeah, of course. There is the other question here. And John, you started to address this. And Ned, I hope that you'll bring it up as well. And before I ask that question, let me just say, we're going to extend a little bit beyond our 8:30 end of show here, folks. We're going to go about another 10 minutes to about 8:40 Pacific time for those of you watching the webcast, because even with that, we won't even scratch the surface of what I hoped we would be able to talk about tonight. We may have to do this another time. So here's the question. Let's say that ITER does achieve exactly what it's supposed to, and this technology continues to move forward. You and I had a conversation about, you know, will this, though, someday result in a technology that is economical enough that it can compete with other sources? The range of renewable and carbon neutral technologies that are now also coming along, you know, just to mention solar, just to mention one of them.
Well, I think John already touched on the challenges very, very accurately that face fusion becoming economical. I'm quite confident that we will produce fusion energy. I'm far less certain whether it will become a technology that is really viable economically. And honestly, one of the interesting things about that ITER video at the beginning was how really smart people like Lord Kelvin did a lousy job of projecting the future. And I'm not as smart as Lord Kelvin, and I'm reluctant to say exactly how we'll be getting our energy 50 years from now.
Ned, we haven't heard from you in a long time. I apologize for that. Please address that. The eventual generation of power, perhaps around the world, the potential of fusion to be a competitive technology.
Well, I'm confident that the developments in materials, computing, and instrumentation are going to allow us to gain a tremendously greater understanding of how do things work, how don't they work, and then based on that understanding to work our way around the problems. So I'm an optimist who says that the human mind is capable of addressing problems and solving them. And I think that the capabilities that I mentioned of computing and instrumentation and the like are really the keys to being able to address the challenges that we will face. And if you look at the activities that John Parmentola talked about, for example, we have to come up with ways to make materials that will handle the large fluxes of neutrons and power. They have to have structural materials which will survive the neutron bombardment. We are getting much better at designing materials sort of from scratch. You know, here at Oak Ridge, we have a program which we call Materials by Design, where we're trying to actually design materials atom by atom to figure out how would you devise a configuration of these atoms that would have the properties that you want. And in the case of a fusion reaction, you want to have structural materials where every atom gets bumped around 100 times and still it's a good structure. So we have to figure out how to do that. I'm convinced that we're going to address those challenges. Some of these challenges are shared with other fields. For example, both fission and fusion have this issue of neutron bombardment. We have these issues of high heat flux in a variety of areas of technology. And I think that there's going to be a synergy which is going to allow us to solve many different problems and have those solutions apply in many different areas.
That's such
I believe materials, computing, and instrumentation are the keys.
And that's such a good point, because one of the sheets of information that your folks at General Atomics gave me, John, had to do with spin-off technology, spin-offs from the research that is underway. Now, I'm used to spin-offs because I'm a space guy, but I never thought that, you know, from this field of fusion research, we would see things advancing in such, disparate areas as cancer treatments, maglev trains. I mean, it's pretty impressive.
Yeah, in the early days of fusion, people had to try to deal with plasma instabilities, which occur over short periods of time. And to deal with that, they had to develop switching technology that could enable them to stabilize it. And that switching technology, which was developed at D3D, actually has found its way into the electromagnetic launch of aircraft from aircraft carriers. So new technology that came out of D3D is going into the USS Gerald Ford, which will be the next aircraft carrier, and that aircraft carrier will no longer launch aircraft with steam catapults. They will be launched with linear motors that incorporate the fast switching technology that finds its origins all the way back into D3D in the early days when scientists had to deal with those problems. Materials, as Ned points out, there are problems in fusion that also have, or challenges in fusion that also are challenges in fission. So, we've been working on the same technology now in fission for about 60 years, right? And there hasn't been any change. We're still working on submarine technology with steam. And so the efficiency of these fission reactors is really very low. It's only about 33%. But we can imagine going to 53% efficiency. And that has a tremendous impact on the economics of any reactor, whether it's a fission reactor or a fusion reactor. But to get to those temperatures, you have to look at new materials. You have to go away from metal. Metals lose their strength at about 700 degrees centigrade. If you're in a reactor, you can easily exceed that. And so that creates issues associated with safety. But now we're looking at ceramic materials, for example, and these materials can maintain their strength above 2,000 degrees centigrade. So this allows us to get the high temperature, but more importantly, what it does is it incorporates safety in it automatically because of the strength that these materials retain.
No Fukushima. For one thing.
You eliminate any Fukushima-type accident with materials like this.
Bill, you're the physicist who's still really doing science, not an administrator as much as these other physicists up here. What are the challenges?
No offense, Ned.
Sorry, guys.
He's right.
What are the physics challenges that remain, and are they basically the same as we faced, since that stellarator was being worked on back in the early '60s?
Well, yeah, there still are many of them. As John mentioned, we have these instabilities, and those are of great concern. I call myself sometimes a pathologist because I will study diseases in there, and we get excited when we make some of these diseases, but the people who are really trying to make the plasma work well want us to get rid of them.
Pure versus applied science.
Yes. So, and so we have different types of instabilities that we worry about. There are kinds that might cause the whole plasma to splat against the wall, and that's a big area of research right now. We call them disruptions. That's an important scientific issue in order to figure out how to run into conditions where the plasma is very hot and dense, so it will be economical, but at the same time will not be at risk of explosively dumping its energy and damaging the walls. There's a type of instability that I work on which involves the alpha particles that was in the video and the slides involving the reaction product. The idea is that those are supposed to be confined by the magnetic field and heat the deuterium and tritium so that new reactions can take place. But sometimes we observe that they cause their own problems and they have instabilities and come out. Actually, the thing I got my prize for was for this instability that came out and ran into the walls and damaged the walls of D3D. So we don't want that to happen in ITER, for sure, or future devices. So that's another scientific issue. Perhaps the biggest one that the plasma physicists are working on actually involve what we call the plasma material interface, because you have this hot plasma in the core. At some place it has to come up in contact with the walls. They might be solids, or perhaps you may have liquid walls, but someplace you have to deal with that, and you have to make sure that the heat is handled and you make the transition to where you can have what happens outside. And that's an enormous area of research, perhaps the most important one that needs to be addressed. It's interesting if you look at the history of research, a lot of the graph that made it go up like Moore's law for computing power actually has to do with discoveries involving the walls themselves. Many of them fortuitous, serendipitous discoveries, but controlling the walls and understanding that plasma material interface is a huge issue.
We are almost ready here to begin taking questions from our audience in the Crawford Family Forum as we near the end of this edition of Next People Science Tomorrow. So please be ready with your questions, and remember what you're going to do is raise your hand and somebody will come over with a microphone. Please make it a question, not a speech, and make it succinct. So we'll do that in just a moment. Ned, just another question for you before we go to the Q&A. Just briefly. You have all these components coming together from all over the world, as we saw in that opening video. Do you have any concerns about whether this big jigsaw puzzle, as it was called, is all going to fit together the way it's supposed to?
Well, it's a concern, but we know how to manage that concern. When we have the big meetings over in France, what we talk about are the performance specifications for each system and also the interfaces. And we pay an awful lot of attention to how is part A going to connect to part B? And is John's central solenoid going to fit in the hole in the toroidal field coils? You know, we do pay an awful lot of attention to that, because that's where the gotchas come and get you. And so what we're trying to do is to have a very strong systems engineering group in France who works out those interfaces, and then we out in the so-called domestic agencies build the parts to those specifications in order that they will fit together. And then there's a very, very extensive quality assurance program where inspectors go out and measure everything and make sure that it is built the way it was supposed to be built, so it will all fit together, so we don't get a rude surprise when it makes it to France.
No feet versus meters problems, as we've sometimes had in the space program.
No, that was pounds versus kilograms.
Okay. Let's go ahead and go to our first question from the audience here in the Crawford Family Forum. Hi, sir. What's your name?
Hi, my name is David Schwartz. I was just curious, why has the Tokamak been chosen as the preferred model to make this breakthrough step versus the facilities like at the National Ignition Facility, which uses a laser bombardment technique?
Which I'm so glad you mentioned NIF, the National Ignition Facility, the one that John began to talk about there that's up at Lawrence Livermore National Labs. But Ned, if you could address that first, why Tokamaks?
Well, first of all, I consider myself to be a fusion person. So I hope that all of the different approaches to fusion will work. And I believe that we ought to be pursuing a variety of different approaches. The inertial approach up at Livermore is quite different from the magnetic confinement approach. And so if we were to find a fatal flaw in either of these approaches, the other would be a completely independent backup. So I believe we ought to be looking at each of these. If you look within magnetic confinement, the reason that we go with Tokamaks are that Tokamaks have the track record. There are a variety of different magnetic confinement configurations, but the one that's ready to proceed to the burning plasma stage today is the Tokamak. And I mentioned that we had a big meeting in Snowmass, Colorado in 2002. One of the questions we asked at that time was, would the burning plasma physics that we study in a Tokamak be applicable to other toroidal configurations? And the answer was yes. And they'd be more applicable the closer they were to a Tokamak configuration. And so the approach that we're taking is to try to produce a burning plasma in the way that we know how to do it best today, which is a Tokamak. And that physics that we learn using that best vehicle today will be applicable to future configurations, be they stellarators or other toroidal configurations. And so the reason we do Tokamaks today is that they are the leading configuration today. They may not be the leading configuration of the future, but they are the vehicle by which we will be able to study burning plasmas today.
And I don't know if you could see, but your colleagues here on stage were nodding vehemently along with your comment. John, I want you to say something about NIF in a moment, but Bill, did you have a comment about that? You also...
Ned's answer is excellent.
Okay. Just
I
say...
mean, let me add one other thing. So he alluded to this, but some of these other configurations are much more attractive from the standpoint of engineering. For example, some of my colleagues at UC Irvine are working hard on something that's called a field reverse configuration, which has certain advantages in terms of maintenance. But of course, its huge disadvantage at this point is that the plasma that it makes is vastly inferior to the plasmas that we have in Tokamaks. So it's not ready, just as Ned said, it's not ready for something like ITER. And it needs further, it's a line of research that deserves and warrants further investigation, but it's not ready for this next step. And I do agree that what we learn from Tokamak, from ITER, will be many of the things that we learn, such as these plasma material interface issues, those are directly transferable to any magnetic fusion concept.
John, can you in 60 seconds tell us what NIF is about? I know General Atomics is contributing to that project.
Yeah, the one thing I wanted to say, though, is in order for a tokamak to be practical, you have to learn how to work on a donut, right? You got to get inside the donut, right? And take all the stuff inside the donut out and put it back in again. So that's a practical problem we have to figure out and how to do it efficiently. Now, in regard to the National Ignition Facility, the first thing is the National Ignition Facility wasn't set up initially as a means of producing energy. It was a part of what's called a stockpile stewardship program that really has to do with understanding nuclear weapons without testing them, okay? And so now, of course, it doesn't take much in logic to figure out that if I can get a burning plasma through laser-driven fusion, then I could possibly extract electricity like I would from a magnetic fusion facility, because it's the same physics, basically. You're generating high-energy neutrons that then, and alpha particles, which you'll then try to capture the energy through similar means that you would through a magnetic fusion facility. The thing is, the National Ignition Facility is what I call a digital version of fusion. It's on, off, on, off, on, off. Because you have to inject the capsules into it, and it's a remarkable thing to go through the reasoning and the timing and the accuracy that will be required, although it's not impossible. It actually is practical, where you have a very tiny little target that's about the size of a pencil eraser, and inside that little can, it's about the size of a pencil eraser, is a peppercorn size sphere that contains the fuel, the deuterium and tritium that we've been talking about, inside the peppercorn, but it's frozen, so get it dense. And then you have to take this little thing with a special kind of injector that actually General Atomics has been working on. It's a magnetically guided gun to shoot it into the chamber and then be able to detect the holes on each end of the can with both spatial precision and timing, so that you can have 192 laser beams go in through one hole, and 190, not 192, it's
96. A lot of big damn lasers.
96 going through one hole and another 96 going through the other hole, such that it impacts the inside of the can's walls to create a very hot plasma that emits X-ray radiation that descends on this little tiny little peppercorn and hits the surface, and it essentially explodes the surface and causes the material to compress to initiate fusion.
It sounds crazy, but it works. They're doing it in Northern California.
And they're doing it in Northern California, and we're about a factor of 2 shy of the neutron yield that's needed to indicate that we've actually achieved fusion.
Not much, not much.
Burning plasma.
We're going to try and squeeze in 2 more questions here, so we'll have to make our responses real quick. We've got somebody way in the back there. Hi, sir.
Hi, I have a question about lithium. Global lithium production is pretty limited right now. It's about 700 kilotons. How much lithium does one of these reactors consume, and how does it compare to other applications?
And are we talking about how much one might consume someday, right? We're projecting out here. Ned, is that something you can address?
Well, I think John talked about some of the numbers, but if you look at the amount of lithium that is in the oceans, that's one source, and that's enough for thousands and thousands of years of worldwide energy production. And then there are other sources, more land-based sources. But John was citing many of those numbers. Even though people are going to be wanting to put lithium into the batteries of their phones and their laptops and the like, I think there's going to be plenty of lithium to produce energy through fusion.
I've got some lithium here in my lap running this thing. Let's go to another question very quickly. Hi, ma'am. What is your name?
My name is Libby Halevi. And my question is, first, I have 2 questions. First is, how in the world could KPCC, a trusted news organization, put together such a one-sided presentation on nuclear without a contrary voice in it? And my other question is, given that nuclear is perfectly safe until it is not, what, if any, unintended consequences, scenarios, and worst possible credible disaster scenarios, as was done at the beginning of the nuclear age, have you done about this technology?
So we get to the fear factor. And I would have to say the confusion, once again, between fission and fusion. They are very, very different, are they not? Bill, you want to say something about this?
Well, I'm not going to address the KPCC part. But, well, I think that's a good point, is that there is a distinction between fission and fusion. One thing that I quibbled with about the ITER video at the beginning was it said no environmental impact or something like that. That's crazy. Every form of energy has some adverse environmental impact. The question is mitigating those and minimizing those environmental impacts. We anticipate that in a fusion reactor, we will have radioactive waste. It's possible that it will be 1% of the kind of radioactive waste that you would have in a fission plant. And we won't have the possibility of meltdown. So the safety factor is great. I mean, one of the reasons that I went into fusion research and have devoted my career to it is I am an ardent environmentalist, and I see this as a possibility for something that will have a huge impact, a beneficial impact on society and be great for our environment. But it's not perfect. Everything has adverse environmental impact. I mean, that site you saw in ITER, it probably was a lot nicer before they went in there and bulldozed it.
Yeah, well, let me point out one thing to you. So if you remember the number I cited about the world needing 400 billion watts of electricity per year? Per year? Okay.
Ma'am, please.
So I'll give you an environmental impact. If you were to do that with windmills, you would eat up 30% of the land area of Italy a year. A year. Okay? So trying to do this kind of thing with that kind of technology will have an environmental impact. You will eat up that land. You will disturb everything in its path by laying down these kinds of solutions. So anybody who thinks that any of this comes free is dreaming. Okay? It doesn't.
There is one more video that I want to show you. It lasts only a couple of minutes, but I think it's important because it lets us hear from some young people. And so if we could run that now. These are students who are serving summer fellowships, undergraduates, working with the D3D Tokamak down in La Jolla.
Hi, I'm Laura Bergston. I go to Dartmouth College, and I'm from New York.
All right, Dartmouth, I've been there. Nice place, yeah.
Hi, I'm Cole Stevens. I go to Columbia University. I'm from Seattle.
I'm James Penna. I'm from New York as well, and I study physics at MIT.
So it's really great to be a part of a huge experiment that does so many different things and tries to learn a bit about a really important idea that could change the world potentially.
It's a follow-up of like both fluid physics and electromagnetism, and those have always been my favorite subjects in college and high school, so I think this is like one of the best things I could do.
Well, I always joke with people that when I wanted to study fusion, it's, help figure out fusion and save the world. Really, as a physicist and a scientist, I feel that there is really no more important problem that we could be working on right now than solving fusion.
I see it coming, at least within my lifetime, maybe within a few decades, and I think that, there have been like obstacles along the way, issues that develop as we, try to keep working on this, but that's part of the scientific process, and we need to keep working at it and keep raising people like us who are young and have them be interested in not only science but interested in global problems like this.
You getting hope from what you've seen here?
Definitely, and I think it's a really exciting time because never before has huge experiments like ITER, the Large Hadron Collider, anything like these ever been put to the test. So it's exciting to see what they're going to come up with, what they're going to find, and I think there's a huge amount of hope for what they'll discover.
I know you find it exciting because you're hoping to work on ITER, it sounds like.
Yes, I think that, it's not a question of if, it's definitely a question of when. And I definitely see it coming soon. We just need to keep throwing money at it, keep throwing resources at it, keep throwing talent like us at it, and it's going to come. It's inevitable.
We are out of time. I hope you'll help me thank three terrific guests. Ned Sotoff of the U.S. ITER Project, John Parmentola of General Atomics, and Bill Heidbrink of UC Irvine. I'm also grateful to all of the good folks here in KPCC, Southern California Public Radio's Crawford Family Forum, who make it so easy to sit up here and talk about science. Janice Watchie-Hurst is co-producer of Next. Dave Lost Moon McKeever is our technical director. Haley Waters provided great production support, as did Carlos Hernandez, a new intern here at Southern California Public Radio. The man who fuses science, art, and a certain savoir-faire, the managing producer of forum programs and live events for KPCC, is John Cohn. Thanks for joining us, everybody, both here in the forum and out there watching the webcast. The next event is almost upon us. It's already at capacity here in the forum, but you can watch the live webcast on Wednesday, July 9 at 7 p.m. as Bill Nye, the science guy, and I return to the forum on behalf of the Planetary Society, and we will be talking about Light Sail, the solar sail project from the Planetary Society, and a big announcement, basically the beginning of a countdown. You can check it out at kpcc.org. Please have a great evening and an even better future. Thanks for coming. Good night.
Before you go, I think the lady with the question about whether or not, why we weren't talking